All right, let's get started. This is our last slide from last time, I think. Or maybe I snuck in something else. But we had the fundamental theorem of invertible matrices from last chapter. And now that we introduced eigenvalues and determinants, we added a couple of more things here for our criteria for an n by n matrix to be invertible. And one, we have to have the determinant to be not equal to 0 for this matrix to be invertible. And then the second is that we had an eigenvalue of 0 in one of our examples, and it turns out that if you have an eigenvalue of 0, then that's not good for invertible matrices. So you want to make sure that your eigenvalues are all non-zero. So this is a list that I think we're gonna continue to add a couple more here as we go on. To have a big list of things that are all equivalent for invertible matrices. Now, our next theorem that we want to add on not quite yet. The stuff that he was doing on the video is actually next section. If we have a square matrix and we have eigenvalue and eigenvector lambda and x, then lambda to the nth power is going to be an eigenvalue of the matrix A to the nth power. And you're going to continue to have the same eigenvector x. So that's kind of interesting, right? If you have an invertible matrix, then 1 over lambda is an eigenvalue of A inverse. That's another interesting fact. And then the last one looks like it's very much like the first one. What's the difference? So it kind of combines A and B together as powers and inverse, powers of inverses and things like that. So I think it'd be nice if we do an example of this. So let's see. We should do it for a 2 by 2 matrix that we can easily compute. And let's see, I don't have any examples. See if we could take that book and find some examples. Let's do number 2. So let's take this and then find out its eigenvalues and eigenvectors, and then let's take it to the second or third power and then find out its eigenvalues and eigenvectors of that. And then I may use Mathematica to to help us do some calculations here. But let's actually do the eigenvalues and eigenvectors by hand, because this would be a good exercise for doing stuff like that. So, do you remember how you start off finding the eigenvalues and eigenvectors? Not multiplied by the identity. So A minus lambda I. Something like that. Anyways, you find a characteristic polynomial, right? So the characteristic, find in null space, find a characteristic polynomial. So we have, this is A, lambda I is lambda in the diagonals and 0 everywhere else. So 1 minus lambda minus 9, 1, and negative 5 minus lambda. Say it again? Yeah. Yeah. So anyways, if we can find the determinant of this, this is our characteristic polynomial. So determinant of this is equal to 1 minus lambda, negative 5 minus lambda, minus negative 9. And we want to find out the solutions for this, so we need to multiply everything out. Minus 5 minus lambda plus 5 lambda is plus 4 lambda. Negative negative is a positive, and the squared plus 9, so that's a 4. And if we set the characteristic polynomial equal to 0, we can find out lambda. I think this is lambda plus 2 squared. So lambda is equal to negative 2, is that right? So it has an algebraic multiplicity of 2. Right. So if we have this as your lambda, we want to find out our eigenvector associated with this eigenvalue. So we got lambda is equal to negative 2. Let's put negative 2 into this equation up here on top to find our eigenvector. So we have 1 minus negative 2, 3. Minus 5 minus negative 2 is negative 3. Is that right? So 3 minus 9, 1. Minus 3. And then if you try to find the null space of this, it'll, because you want to find the vector set equal to 0, you'll see that they would, undo each other or cancel out or whatever. So you have a row of zeros, and then you basically have x minus 3y is equal to 0, so x is equal to positive 3y. And if y is equal to t, x is equal to 3t. So then your corresponding eigenvector, call it x, is equal to 3, 1. Is that okay? So this has geometric multiplicity also. This has a geometric multiplicity of what? Yeah. Well, it's considering that particular eigenvalue. So it's just one eigenvalue. Yeah.
Sorry, what's meant by that term?
The algebraic multiplicity is the multiplicity of the characteristic polynomial, the root that we got there. So since this factored out to lambda plus 2 squared, then that has algebraic multiplicity of 2. It's however many times that multiplicity. Well, multiplicity of something, if you have, in algebra, if you have x plus 3 squared times x minus 2 to the 4th times x is equal to 0. If you have this equation and you solve for this, this is x is equal to 0 with multiplicity 1. This is x is equal to negative 3 with multiplicity 2. And this is x is equal to 2 with multiplicity 4. Multiplicity 2, multiplicity 4. So that's algebraically, that's the multiplicity. Geometrically, the multiplicity is how many eigenvectors are associated with that one particular eigenvalue. Roman?
What's the notation put in to signify eigenvector?
Oh, that's the eigenspace. Eigenvector, usually they just say x, a vector, or v, and then they just say it's associated with this.
Okay, so for eigenspace.
For eigenspace, that's when you get to use the E notation. So eigenspace is going to be E sub whatever the eigenvalue is, in this case is negative 2. And this is going to be the span of, in this case, only one vector.
So if you have a 2-by-2 matrix and you want a geometric multiplicity of 2, you have an algebraic multiplicity of 2. I mean, is the only way to get it to have a minus lambda be like some multiplicity of identity or something? How would you get a two-dimensional space out of that?
I don't know if you can for 2-by-2 matrices. I think that only works for matrices that have more than.
If a minus lambda I were equal to I, right? Then you can get 2.
The fundamental problem is that when you're solving for your null space, you can only have one parameter. So at most, you can only have one eigenvector or one basis that's within your space. So I think you would need at least two vectors.
Well, maybe that's it. The book had cases where there was an algebraic multiplicity, it's more than 2.
Yeah, but it's all higher.
Geometric is more than 1, but I guess that means you've got something else
You got something else. Yeah, you got another.
at the same time.
You have another eigenvalue
Yeah,
to work with.
right.
So, all right. Now, the whole point in doing this is for us to try to see if we can use this example to verify this theorem that says if we take this matrix A and we raise it to the second or third power, then our eigenvalue would be negative 2 raised to whatever power it is. Okay, so let's see if that actually is true. Let's take A. how high should we bring this power to? To the fourth power? I'm just going to use Mathematica to do it anyways. So let's take this matrix, 1 minus 9, 1 minus 5, and let's take this to the fourth power. What is it, matrix power? And to the fourth power. So this is our new matrix. And let's find the eigenvalues of this. Should we do this by hand or should we let do it? Are you guys comfortable with finding eigenvalues and eigenvectors? Okay, so let's just have Mathematica do it. So let's find the eigenvalues. Before we find the eigenvalues, what should we expect the eigenvalues to be? The same?
No, the eigenvalues to the power.
To the power. So what's 2 to the fourth power? 30. 16. What do we need for this? We just need the matrix. Yeah, we just need the matrix. So here are your eigenvalues for this matrix, turns out. So we got lambda in this case, -2 to the fourth power, as verified. And then eigenvector, it has to have a corresponding eigenvector. So let's see what the eigenvectors are. Just need the matrix, just need the matrix. 3, 1, and then 0, 0, which we won't consider. So the eigenvector corresponding to this eigenvalue is also 3, 1. I think so. Yeah, we got 3, 1 before. Technically, it's in the null space of everything, and just to correspond or to have 2 eigenvectors. Yeah. Well, it's not quite the empty set. This is an actual vector 0, 0. So vector 0 that would correspond. So because this has geometric multiplicity of 1, it just means that's the dimension of the null space. So they just throw in that other vector to have it the same amount, same number.
Is that a requirement for some, like it had to go past through 0, 0?
If it's a space, yeah, it has to pass through 0, 0. But the thing is that if we had different eigenvectors, then this probably wouldn't have been 0, 0. It would have been something else. Well, because this is a 2 by 2 matrix, it's expecting to have 2 eigenvectors. It just throws it in there by default because there's only one that exists. So if we add 2 legitimate eigenvectors, then the second eigenvector would have been whatever that is. So this is verified. Now let's take a look at the inverse of A. You can find the inverse real quick, right? Yes. You can have Mathematica do it, but we will have Mathematica do it. But how do you find the inverse of a 2 by 2 matrix? A inverse equals what? 1 over the determinant, which is minus 5 plus 9, 4. Switch the diagonals, negative the wings. So this is your inverse. And if we were to find the eigenvalues and eigenvectors of this inverse, we should get what should we get for our eigenvalue? What should we get for our eigenvalue? No, this is not to the fourth anymore. This is the inverse. So according to our theorem, your eigenvalue of the inverse should be the reciprocal of your current eigenvalue, so negative a half, with a corresponding eigenvector that's exactly the same. So let's ask Mathematica to compute this for us. First, let's find the inverse of A. Oops, I don't want to do matrix form. So this is everything multiplied by 1/4 that we got. And then we want to find the eigenvectors, eigenvalues first. So negative a half, as we expected or should have expected, and the eigenvectors are again 3, 1. So this is by no means proof of what we're working on, but it verifies the theorem that we're looking at. We haven't proved much lately in this class, huh? But this verifies our two parts of the theorem. A third part just goes for negative powers, and so that's a combination of an inverse and a power. So I won't do that. Any questions about this? Yes. Oh, that was a determinant. So maybe if we do the, I don't think this will help, minus 5 minus negative 9. But that is the determinant. That's the determinant of A, and there's a formula that says A inverse is equal to 1 over the determinant of A. And this is only for a 2 by 2 matrix, and then you switch the diagonals and negative the wings. If you can understand that. So there's a quick way to find the inverse of 2 by 2 matrices. Questions? Yeah. Yeah, we were talking about that, and I think because this has a geometric multiplicity, this has a geometric multiplicity of 1 and an algebraic multiplicity of 2. Since we're looking at a 2 by 2 matrix, we're looking to fill in, the computer is looking to fill in the second vector, but really there's only one eigenvector that's involved in here. The only eigenvector that's involved here is 3, 1. So in a way to fill in our second vector, the computer puts in a 0, 0. Actually, that's an interesting question to see what happens with MATLAB if you try to do this in MATLAB and find eigenvalues and eigenvectors of it. So I wonder if that's a thing to do. Somebody can try to do it and let me know. And then I'll try to do it also. All right. So now let's take a look at the last two theorems in this section. The last two theorems basically just continue to talk about the matrices raised to powers and stuff like that. Let's start with this one. You have an n by n matrix, a square matrix, and then eigenvectors with eigenvalues. They call eigenvectors this time v, and eigenvalues are still lambda. Notice that this m here is not the same as n. That's because we possibly could have multiplicity of 2 or more for one of these eigenvalues, so we're not going to have n distinct eigenvalues. We could possibly just have m of them. Now, if x is a vector that can be expressed as a linear combination of the eigenvalues, or eigenvectors, sorry. If x is a vector that can be expressed as a linear combination of the eigenvalues, eigenvectors. Let's try that again. X is a vector that can be expressed as a linear combination of the eigenvectors, v1 through vm. This should be m. Then if we take that matrix A and raise it to any power, positive power, actually negative also, if we could raise it to any power, then it could be a linear combination of these eigenvectors. So this is almost like saying, as long as we have this vector x that we can write with v1 through vm, then it's almost like having it's like using the vectors, the eigenvectors, as a basis for this vector x. I don't know if we want to mess with this too much. Do you guys have any questions like this in the homework that came up?
There are two homework problems. One of which involves finding a to the 10 power x and a to the 20th power x respectively, and they involve either a 2 by 2 matrix or a 3 by 3 matrix.
3 by 3. Okay, let's take.
And they both. You're supposed to find a while you're given a set of eigenvalues and eigenvectors and the x vector.
There's one funny formula way to do one of them.
Oh, that was fun.
It's so much yeah, I didn't get that. Is that going to be on the test?
Is it going to be on test? I don't know.
Kramer's open, but he lost
Oh, let's do number 4. Oops. Yeah.
So your system, you have come with green numbers, like that.
Green? Red numbers.
Why come with geometry?
Which version did I need to buy?
All right, let's take a look at this problem and see how we can apply that matrix. You can see we don't know what the actual matrix is. A is a 3 by 3 matrix, but it gives us the eigenvalues or eigenvectors and eigenvalues for this. And then they give us a matrix X. So the only thing we need to be careful about is that X is actually a linear combination of V1, V2, and V3. So how do we find out if X is a linear combination of that? Well, we can try to set it up so that X is equal to some constant times, and these aren't the eigenvectors, these are just the constants to make the linear combination. And C2 times 1, 1, 0, and C3 times 1, 1, 1. So if we can eyeball it, that would be great. Otherwise, we'd have to do some system of linear equations business. 5, 4, and 5. Can we just from here figure out what C1, C2, and C3 might be equal to? So 1 minus 1 and 5, that would work? All right, good. So we got C1, C2, and C3. And if you weren't able to do that, you just have to make this a matrix coefficient system and then do the row reducing business. Which, if you look at these vectors, it looks like it's diagonal anyway, so it'll be easy enough to do. Anyways, we got this for our C1, C2, and C3. And now we have these values over here. According to our theorem, this is supposed to be equal to a to the 20th times the vector x is supposed to be equal to the C1 times the corresponding eigenvalue raised to that same power times our vector V1. Right? That was our theorem over here. Oops. Our theorem over here. Plus C2 lambda 2 to the same power vector V2 plus C3 lambda to the same power V3. Lambda sub 3, the third eigenvalue. All right, all we got to do is put in our values then. So we got 1 for C1. We got negative a half raised to the 20th power. And then we got the vector V1 plus C2 is negative 1 times, we got lambda is 1/2. This lambda 2 is 1/2 raised to the 20th power 110 plus C3 is 5 times, and then the last eigenvalue is 1, and then this is 1, 1, 1. So I suppose we just need 2 to the 20th power. Should I know that? No. That's a big number. So it looks like this is going to be, let's see. I'll just call it positive 1 to the 2 to the 20th power, or 1 over 2 to the 20th power. And this is a minus, let's just say a plus, and then negative 1 over 2 to the 20th power, negative 1 over 2 to the 20th power, and 0. So it looks like the top one will disappear. And this is just 5, 5, 5. So simplifying this, it looks like we just get 5 on the first component, and this is 5 minus 1 over 2 to the 20th power, and then 5 in the bottom. More than a million. So that probably rounds off to just 5. That's the answer. Oh, I got the version that has the answers. Oh, here it goes. That's the answer. Okay. So this is making use of that theorem with if you know your eigenvalues and your eigenvectors, then you got a matrix that you want to apply to a particular vector, but you're going to take that matrix to some power, then you can do this shortcut. Again, you have to know the constants for the linear combination business. Okay? Any questions? What? This is problem number 4. Problem number 2. This one? Kind of like the same thing.
Except it's 2 by 2.
Yeah, except it's 2 by 2. So just try to figure out what the constants are to multiply this, and then it's basically the same thing that we did, except it should be easier, right? Because it's 2 by 2. Kaylee Hamilton. Okay, let's do it. This theorem can be used to calculate the powers of inverse of matrices, kind of like the same as that thing that we had earlier. This thing. All right. So it's easy to see by continuing in this fashion. Oh, here. So this is the first power, or the second power looks like this, and the third power looks like this. Easy to see by continuing in this fashion. We can express any positive power of A as a linear combination of I and A. And so if we have to the negative first power, we have this linear combination. So for matrix A, use the Cayley-Hamilton theorem to compute A squared, A cubed, A to the fourth by expressing it as linear combination. So let me move that. notes are going to be a mess. So when we find our characteristic polynomial, I don't know if you guys have seen this yet, but when we find our characteristic polynomial, we're always going to have a positive lambda squared. So it's I minus lambda business, or A minus lambda I. And then the lambdas and the diagonals will always be, for a 2 by 2 especially, but also for any size n matrix, you're going to have a lambda to the nth power as your leading term in your polynomial. So if we can figure out what our other coefficients are, we can kind of set up our lambda, or find our a squared and a to the fourth, a cubed a to the fourth, and stuff like that. So we find out our characteristic polynomial. We want the determinant of a minus lambda I. So a is this, lambda I is just lambda, so we got 1 minus lambda, -1, +5, and then 3 minus lambda. And the determinant of that is 1 minus lambda, 3 minus lambda, minus -5, which, if we multiply it out, we're going to get lambda squared. Let's see. The middle term is -1, -3, so -4 lambda. So that's going to give us our a value. And our last term here is 3. And then you add 5 to it and you get 8. So in our case, a is equal to -4 and b is equal to +8. Right? So if we just simply use this formula, we get a squared is equal to -a times the original a minus b times the identity matrix. So what is that? This is +4 times a. I'm just going to go on and multiply everything by +4. So 4, -4, 20, 12. And then 8 times the identity matrix is just 8's in the diagonal. And we do the subtraction, we're going to get -4, -4, 20, and +4. Okay? We should verify this. If you do it by just matrix multiplication, 1 minus 1, 5, 3. 1 minus 1, 5, 3. So first row times the first column, got 1, 1, -4. First row, second column, -1, -3, -4. Second row, first column, we got 5 plus 8. No, 5 plus 15 is 20. Second row, second column, -5 plus 9, -5 plus 9. 4. Thanks. And that checks out. It's the same. So if you're doing this problem and it's not asking you to show the work, right? If you're doing this problem, you could have just did the matrix multiplication and given the answer for a squared. But you should see how I thought this was a little bit easier. Do you think? And especially if we're going to do it to the third or fourth power, then it could be easier. So to the third power, according to this formula over here, we have a squared minus 4 squared minus b, that's minus 8, times a, plus a times b times identity matrix. That is 16 minus 8 is positive 8. A negative 32. I. So this would be 8 times A. 8 minus 8. 40 and 24. Minus 32i. So we got 8 minus 32 is negative 24. Minus 8. 40 and negative 8. So that's a cubed. Okay? So they want us to find a to the fourth. They didn't do a to the fourth for us, huh? Suppose we just do the same thing over here. So let's see if we can come up with a formula for a to the fourth. Well, we can look at a to the fourth as a cubed times a, or we can look at it as a squared times a squared. Either way, I think, would be reasonable. One way would probably be easier. Well, let's see. A to the fourth is let's look at it as a squared times a squared. And a squared is equal to minus little a times big A, b times I, times itself, right? So let's FOIL it out. This becomes positive a squared, capital A squared, minus, so negative a, negative b, so that's a positive, 2ab, a times identity, which is just a, and then the last term is b squared, I squared, which is also the identity. So we're just foiling this. And we have a squared, So a squared is equal to this. We don't want any squares, right? The whole point of this is to simplify it with just a's and i's. So I'm going to replace this a squared again with minus a minus bi. And I'll simplify this business over here. This is just going to be a 2ab capital A, and I is identity matrix, so it'll get multiplied, and then you just have the identity. And we have b squared, I squared is just I because it is the identity. And then we're going to get negative a cubed minus ab. Oops, sorry. A cubed a minus ab I a squared b because of that a squared plus 2ab capital A plus b squared I. All right, I think we finally got it. If we combine all the terms with an a in it and all the terms with an I in it, we're going to get minus a cubed plus 2ab a plus, and then I'll put this in parentheses because this has a negative, negative a squared b plus b squared multiplied by the identity matrix. So the idea here is to take a power of a matrix and have it as a linear combination of A and I, the original matrix and the identity matrix. Then you can just work with these constants, the A and the B constants put together as the coefficients for that linear combination. Do we need to do that? Yeah, you guys can figure that out. So to find the fourth power, just use this formula. I'll start it. A to the fourth is going to be negative, and then little a is negative 4 to the third power plus 2 times a, and b is equal to 8. So this is just going to be a number after you simplify it, and then you multiply that by the matrix A, and then you'll take minus a squared times b plus b squared and then you'll put that in the diagonals because you're just going to multiply it by the identity matrix, and then when you work all the stuff out, it should be easier to add and multiply. Or, yeah, this is just a scalar multiplying a matrix and then just adding two matrices, which is a lot easier than taking something to the fourth power. Be interesting to keep going with this to the fourth, fifth, sixth power and see if there's a pattern develops with this linear combination, because it's all about just A's and B's, little a's and little b's, being multiplied with capital A and capital I. All right, just as last one bit of information to close off this section, the last theorem here says that if you have eigenvectors, the combination of all your eigenvectors along with any eigenvalues, but just the eigenvectors are all linearly independent. So this becomes a little bit significant when we're dealing with finding the eigenspaces. It turns out that if you're finding eigenspaces for each of these eigenvectors, they're all going to be different spaces, and then you put them all together, they're all going to be linearly independent. So on an n by n matrix, if you have as many eigenvectors, as many eigenvalues as you have the dimension of the matrix. If you have a 3 by 3 matrix and you have 3 distinct eigenvalues with 3 distinct eigenvectors, then all those eigenvectors will span all of R3. Okay, I think we can be done here. So next time we'll finish off chapter, I don't know if we'll finish off chapter 4 and the last section in chapter 4 in one lecture, but we'll try to see if we can get through there. You're welcome.